Today we are going to be talking about the concept of mesh analysis. This is extraordinarily similar to the nodal analysis that we did on Wednesday, except we are going to be using multiple applications of Kirchhoff's voltage law to solve for unknown currents, whereas in nodal analysis, we use multiple applications of Kirchhoff's current law to solve for unknown voltages. So the circuit that we are going to use to introduce the concept of mesh analysis will be this guy, where we'll have 10-volt source, a 9-ohm resistor, a 2-ohm resistor, a 4-ohm resistor, we'll have a 5-ohm resistor down here, a 1-ohm resistor, 7-ohm resistor, 3-ohm resistor, and 8-ohm resistor, and finally down here, a 6-ohm resistor. So our first step in the mesh analysis process will be to identify our meshes. I know that it's been quite a while since our very first lecture in this class, but does anybody remember what a mesh is? Because it was introduced way back then. A mesh, that's the start of it, okay? A mesh is any loop which does not contain a smaller loop. So in this case, we would have this mesh that I'm outlining in red. Let's do this guy here in blue. And let's have this guy here in orange. So these are our meshes. And our second step is to assign mesh currents. So what that means is that we are going to treat each one of these meshes as if they have a current. I'm going to call this one here IA, this one IB, and this one IC, circulating around each of these meshes in the direction that I have indicated. I always write my meshes such that the current flows clockwise around the path. There is nothing stopping you from writing your meshes flowing counterclockwise or some combination, so some clockwise, some counterclockwise. I would argue that if you want to mix things up, you're perfectly within your right to do it. There's nothing mathematically wrong about it. But the algebra that's going to get involved is going to be very confusing or potentially very confusing. So I would suggest sticking to having all of your currents flow in a single direction, whether that be clockwise around their meshes or counterclockwise around their meshes. All right, so our third step here will be to write controlling variable equations in terms of mesh currents. Now, because we don't have any dependent sources, we actually won't have to apply step number 3, but I put it there because that's one of the easiest things to forget to do. So I try to put those easy to forget steps early on. And then our 4th step is where the bulk of our analysis will come in. So step number 4 will be to write a KVL equation for all meshes. And so I'm going to write these KVL equations pretty much exactly how I've always done it. I'm going to start in the bottom left-hand corner, and I'm just going to follow the current around its loop. All right. So our KVL equation for mesh 1 is going to look something like this. If I start in the bottom left-hand corner, the first thing I see is the negative polarity terminal of the 10-volt source. So that's going to be negative 10 volts. Then I see my 9 ohm resistor, and that 9 ohm resistor is carrying a current of IA. Then I see my 2 ohm resistor. And so let's stop for just a moment to describe what's happening here, okay? So we're following mesh current IA around its clockwise path, okay? So IA is kind of our direction of reference here. Well, in the 2 ohm resistor, we have a current of IA flowing down, but we also have a current of IB flowing up as IB circulates around its clockwise path. So the total current that is flowing through the 2 ohm resistor is some combination of IA and IB. And what that combination is depends on which current we're following. So when we're following IA around its path, it's going to get the positive sign, and the current that is in the opposite direction is going to get the negative sign. So we're going to have IA minus IB. We move down to the 4 ohm resistor, and it's going to have IA minus IC because it has an entirely different mesh current opposing the flow of IA there. And then finally, we will have our 5 ohm resistor, and it's only carrying current IA. And because we're writing a Kirchhoff's voltage law equation, we set this guy equal to 0. So those are the rules for writing our Kirchhoff's voltage law equations. Bradley. No, not at all. So these mesh currents only flow around that clockwise path. So they don't ever split or anything like that. They just flow in those little loops. Exactly right. So whenever we have 2 currents flowing through a resistor, or really any element, but right now we'll restrict it to resistors, we're going to see that if we write all of our currents either all clockwise or all counterclockwise, we'll see opposition, and so we're going to wind up with a minus sign in the middle. All right, so let's look at our mesh 2 equation. Now that I believe the rules have been established, I'm going to ask you guys to help me. So if I start here at the node where the 2 ohm resistor, 3 ohm resistor, and 4 ohm resistor are connected, and follow mesh current 2, or mesh current Sorry, I've labeled these poorly. This should be mesh A and mesh B. I don't know why I chose to use 1 and 2 when I've obviously labeled them with letters. So I apologize for how confusing that probably was. But anyway, I'm going to follow mesh B around its clockwise path. So McKinley, what should I have in my KVL equation? Right, so we see the 2 ohm resistor first. Exactly right, IB minus IA. So when we're following mesh current B, it's going to get the positive sign, and anything in the opposite direction of mesh current B will get the negative sign. So as we follow mesh current B, it flows up through the 2 ohm resistor. IA is flowing down through the 2 ohm resistor, and that's why we have IB minus IA. Abigail, keep it going. Tell me what's next. Plus 1 ohm times IB. Thank you, ma'am. Norman, what comes next? 7 ohms times IB. Thank you. And David, what's our last term? Three ohms times IB minus IC. Absolutely correct. And since our mesh current touched 4 elements, we should have 4 terms in our equation. Lastly, we would write a mesh equation around mesh C, or excuse me, Kirchhoff's voltage law equation around mesh C. So starting at this node where the 5, 6, and 4 ohm resistors meet, and following mesh C around its clockwise path. Shaw, what should be my first term? 4 ohms times IC minus IA. Absolutely correct. Avery, what comes next? 3 ohms times IC minus IB. Thank you, ma'am. That's great. Joel, what comes next? 8 ohms times IC. And Nick Duncan, what comes next? 6 ohms times IC. Thank you, sir. So we have 1, 2, 3 equations. We have 3 unknowns. We can now solve this system using our calculators. So I invite you guys to spend the next 2 to 3 minutes doing just that. Yes. For the 6 ohm resistor, so it will just be IC. So Henry asked a good question here. So let's take a moment to think about that real quick. Effectively, whenever we have a component that is on the perimeter of the circuit, it's always going to carry only one mesh current. Only when it's on the inside of the circuit will it have something opposing it, right? So since that 6 ohm resistor is on the outside edge, it can't see anything flowing against it. So it should just be IC. Mm-hmm. Give you guys another minute or so. You can confirm whether your answers match mine, which I've listed up here on the board. All right, so how are you guys feeling about the application of mesh analysis for circuits that only have voltage sources? Hopefully it seems pretty straightforward, right? So let's do what we did last class period and start messing things up by including current sources into our circuits. So let's analyze this guy. Let's say that we have a 5 ohm resistor, 12-volt source. Let's put a dependent current source here, right in the middle. Let's call this 2ix. Take that back. Let's call this 2vx, so that we'll have a voltage controlled source. Let's call this a 10 ohm resistor. Let's call this a 3 ohm resistor. Let's put 4 ohm resistor here. An 8 ohm resistor here. And I'm going to be tricky with you guys. And so I'm going to call this voltage Vx, where the positive polarity terminal is in the top left corner of what will be mesh A, and the negative polarity terminal will be in the bottom right corner of what we will soon see as mesh A. So I've done a couple of things here. The first is that I have introduced a current source smack in the middle of my circuit that we're going to have to deal with. This current source happens to be a dependent source, and I have labeled my controlling variable in a way that is meant to be mildly difficult for you to express in terms of our mesh currents. So let's follow the steps. Identifying our meshes. This is going to be fairly straightforward. There are exactly 2 of them. This one in red and this one in blue. Our next step will be to label our meshes. So let's call this guy in red IA, this guy in blue IB. Our third step will be to write our controlling variable equations. Since we have a dependent source, we're going to have one this time. So let's start with that guy over here. We want to express the voltage Vx in terms of our mesh currents. Anybody have any idea how we might do that? Norman. You're so close. So Norman's jumping ahead a little smidge, but you've almost got it. Kai, what are you saying? Norman was closer. Connor. Which would just be 9IA, so still not quite right. Bradley. Bradley is correct. Negative 9IA. But let's talk about exactly why that works, okay? So that voltage Vx, let me do this in orange, see if I have enough room here, is going to be equal to the voltage drop over the 5 ohm resistor plus this voltage drop over the 4 ohm resistor if we write a Kirchhoff's voltage law equation around effectively the bottom left-hand triangle of mesh A, right? Where since we're just writing a KVL equation, we can take that voltage drop across the middle as part of our loop because we don't care whether or not current flows, we're just adding up. With those polarities defined as positive polarity on top for V5 and positive polarity on the left for V4, a current of negative IA is flowing into the positive polarity terminals of each of those resistors, which is how we get Vx is equal to 5 ohms times negative IA plus 4 ohms times negative IA, which is the exact same thing as negative 9 ohms times AA, which is what Bradley suggested. So that's really about as difficult as I can make a controlling variable be. Something like that, where the simple application of Kirchhoff's voltage law will get you the value that you want. If it had been a controlling current, it would have just been some combination of the mesh currents. Or, yeah. So, step 5 is going to be, so we have step 4, and I'm going to do this South Park style. Put profit with some question marks because we don't quite know what that one's going to be yet. We'll come back to it in a moment. But step 5 is going to be to write our KVL equations, okay, for each of our meshes. So if we try to write KVL at mesh A, what we will wind up getting, we start from the bottom left-hand corner and follow that red loop. We'll get 5 ohms times IA minus 12 volts plus the voltage drop over a current source. We have no way to express the voltage drop over this current source in terms of our mesh currents, right? Even if we tried, right? So some of you might be saying, well, it's just going to be 2Vx because that says that's what it is. That 2Vx is a current. That's a voltage controlled current source. That still tells us absolutely nothing about that voltage drop, right? So best case scenario, we could call this VC CS and move along. Then we would have our 4 ohm resistor multiplied by a current of IA. So set this equal to 0. And when we try to write a KVL equation for mesh B, we're going to run into the exact same problem, right? The first thing we see is that current source over which we need a voltage drop, but we have no way to express that voltage drop in terms of our mesh currents. So we're just going to have negative voltage controlled current source, and then we would have plus 10 ohms IB plus 3 ohms times IB plus 8 ohms times IB is equal to 0. So what we are going to do to avoid this problem is introduce the concept of the super mesh. And a super mesh is just the smallest loop we can take that avoids getting the voltage drop over that current source, right? So for our case, if we took this path that I'm going to outline in purple and wrote a KVL equation, that would completely avoid us ever having to take the voltage drop over that current source, right? We'll find that that path in purple is nothing more than our KVL equation at mesh A added to our KVL equation at mesh B, which is a perfectly acceptable thing to do because 0 plus 0 still equals 0. Right? So KVL at supermesh AB is simply 5 ohms times IA minus 12 volts. That gets us to this point right here. Now we're following mesh IB around. So we'll have 10 ohms times IB plus 3 ohms times IB plus 8 ohms times IB. That gets us to this point here. And now we're following mesh current A back to our point of origin, which is the bottom left-hand corner of the circuit. So 4 ohms times IA. Set this equal to 0. You'll notice that this is exactly KVL at mesh A plus KVL at mesh B. So I'm going to scroll up so that hopefully you guys can see my equation in at least most of the circuit at the same time. And if you have any questions about where any of those terms came from, I'd be happy to answer. All right, nobody seems to be asking any questions. So we have one equation right here, which has two unknowns, right? IA and Vx. We have a second equation down here that has IA and IB, and I'm going to strike through these guys to let us know that we're not supposed to use those. So we have two equations and three unknowns. So how are we going to figure out what our fourth equation is? Well, that's where that step 4 that we glossed over comes into play. Step 4 is write current relationship equations for our current sources. So what I mean by that is I have a current source there smack in the middle of the circuit, right? Kennedy, how much current is that source providing? 2Vx. We'll get to that part in a minute. So just 2Vx. All right. There are two mesh currents flowing through that branch that contains that current source, right? We have a mesh current of IA flowing down and a mesh current of IB flowing up through that current source. So what we're going to do is we're going to say the current that's in the same direction as our current source, which is IB, minus the current that's in the opposite direction of the current source, which is IA, is equal to the amount of current being provided by the source. Does that make sense? Okay. There's our third equation. So we now have three equations, three unknowns, and we can easily solve. So let's take a couple of moments to do that. So we could, if we were so inclined, do substitution here and express Ix in terms of Ia and substitute it in, but because all of our calculators should be able to do three equations and three unknowns, I'm going to leave Ix as a variable so that I don't make some simple mistake in my algebra trying to do that substitution. So I have, for my controlling variable equation, -9 IA plus 0 IB hold on, now I'm confusing myself here. Instead of, so the problem is I have it written as Ix when there's no Ix in the current or in the thing at all. It's a voltage Vx. That's where my dumb mistake was. So sorry, I have -9 IA plus 0 IB minus 1 Vx is equal to 0. In my second equation, I have 5 IA plus 4 IA, looks like +9 IA. I have 10 plus 3 plus 8 IB, so that looks like 21 IB. I have no VXs. And then I have +12 volts, move to the right-hand side. And my last equation, I have -1 IA, +1 IB, -2 VX is equal to 0. And I get -34.483 milliamps, +586.207 milliamps, and Vx as 310.344 volts. And I'm going to go ahead and double check my equation to make sure I didn't make some silly mistake. I got the same results twice. So if I made a mistake, I made it twice. How did you guys feel about this one? Still need another couple of minutes to wrap your head around it, or everything seem okay? All right, so we're going to work one last, oh, sorry, Henry, did you have a question? So what are your coefficients for IA in your first equation? Okay, what's your coefficient for IB? So Vx should be -1. The reason why I say that is because we need to move Vx onto the same side of the equal sign as all of our variables because it's a variable. And so there will be a constant term of 0. Does that make sense? There's likely a similar issue with your third equation as well. So for me, that one looks like -1 IA plus 1 IB minus 2 Vx is equal to 0. Okay. All righty. Any other questions, comments, or concerns regarding this analysis or putting stuff in your calculator or anything? Perfectly okay to have questions, perfectly okay to make mistakes. Lord knows I'm going to make plenty of them in this class. All right. Okay, so we're going to work one more example problem. This guy's going to have multiple current sources. And I'm going to make this problem in such a way that we have a current source on the interior of our circuit, which is what we had here, as well as a current source on the exterior or perimeter of our circuit. And we're going to see how to handle that situation. And honestly, current sources on the perimeter of our circuit are a good thing when we are doing mesh analysis. Right? So this is going to be my new circuit of interest. And let's say that we have a 10 ohm resistor up here, 3 ohms, 5 amps, 2 ohms, 4 ohms, 4 volts, twice IX, which means I'll need to define IX. Here is a 5 ohm resistor. Here is a 6 amp source. And let's call IX the current that's flowing up through the 5 ohm source. Okay. Now, it should be fairly obvious here that this circuit is going to contain 4 meshes. Everybody okay with seeing that? All right. So you might have reservations about analyzing a circuit like this because it's got more meshes than what our calculator can easily handle. But we're going to find out that because we have a current source on the perimeter of the circuit, we're actually going to get one variable given to us for free. Okay. So if I identify my meshes, there's going to be, let's call this guy IA. This guy will be IB. This guy will be IC. not different enough. This guy will be ID. We have steps 1 and 2 already taken care of, right? We've labeled our meshes, excuse me, we've identified our meshes and labeled them all in kind of one go. So our third step would be to write our controlling variable equation. So the variable that is controlling our dependent source is that current Ix. It's flowing up through our 5-ohm resistor. So we're going to have Ix is equal to what? Anybody have any ideas? Six minus IC. That is certainly one way to do it. But it might not be obvious to everyone yet. So let's call it ID minus IC, okay? So ID is the mesh current, or excuse me, as ID flows around its clockwise path, it's flowing in the same direction as that current Ix. IC, as it flows around its clockwise path, is flowing in the opposite direction. And so that's why we get ID minus IC. And just for the heck of it out here, I'm going to go ahead and put in Norman's suggestion of 6 minus IC, because he's absolutely correct. And that's going to lead us to one of our next equations anyway, right? So step 4 would be our current relationship equations. So if we have 2 current sources, we should expect to see 2 equations. Seems fairly obvious, but we could say that ID is equal to 6 amps is one of those equations, right? So as ID flows around its clockwise path, it is flowing in the exact same direction as the 6 amp source. So it must be 6 amps. If the 6 amp source were direction up, ID would be negative 6 amps, right? So anytime we have a current source on the perimeter of our circuit, we are going to just know that that current, whatever current is supplied by that source, is equal to one of our mesh currents. So in this case, that is effectively eliminating a variable. We no longer have to worry about what ID is doing because we know that it's exactly equal to 6 amps, which is reducing the size of our system of equations, right? Let's see, Jacob Darbone, tell me what my other current relationship equation is supposed to be. IC minus IA, absolutely right. As IC flows around its clockwise path, it is in the same direction as the 5 amp source, so it gets the positive sign. As IA flows around its clockwise path, it is in the opposite direction of the 5 amp source, so that's why it gets its negative sign. Thank you very much. All right, so we have our current relationship equations taken care of. So now we need to write our KVL equations, right? So I'm going to do this one in gray. Last time, when we had an interior current source, we had to write a super mesh, right? We had to have a path that enclosed our interior current source. We're going to have to do that again. So that's just going to be a combination of mesh A and mesh C. Like so. So we're going to have a KVL equation at super mesh AC. If we start here, What's that equation going to look like? Anybody? So Mo, if I start at that place where I put a little arrow and I'm following that gray path around its clockwise path, what's the first thing I see? The 10 ohm resistor, right? What current flows through the 10 ohm resistor? IA. Jessica, what do I see next? No, it's fine. So we've gone, let me do this in this color, all right? So we've gone through the 10 ohm resistor. We're now here and we're turning in. We're following that gray path. So what's the next thing we see? Exactly right. 4 ohms times IA minus ID. And since we know ID is exactly equal to 6 amps, I'm going to go ahead and make that substitution in. Oren, what comes next? So we're following that gray path. So we've gone through the 4 ohm resistor and now we're going down. Right, so we're jumping over that branch entirely. Okay, so that's actually a reasonable place to be confused here, okay? So when we use our super mesh, we are avoiding taking the voltage drop over a current source. But in this case, we have a current source in series with another element, okay? That other element, we don't have to worry about the voltage drop over it either. And the reason is, it's effectively already given, right? How much current flows through the 2 ohm resistor? Exactly 5 amps because they're in series. So we don't need to include that in our calculations. Skipping over in our our KVL equation doesn't throw away that information. It's just buried in our current relationship equation. Okay, so that's why we get to avoid that path. So if it's an interior current source, even if it's in series with other things, we still go around it. Okay, so we're heading down after we see the 4 of Abby. So yeah, the super mesh is formed between IA and IC because it's the smallest possible combination of meshes that avoids taking the voltage drop over that 5 amp source. Okay, so our super mesh will always be the smallest combination. So effectively, if the 5 amp source is in between mesh A and mesh C, then our super mesh will be mesh A plus mesh C. All right, Oren, sorry for interrupting you. Five ohms multiplied by, did you say IA? Mesh C is the current that's flowing down through the 5 ohm resistor, right? So even though it's a super mesh A and C, we still have to take account of which part of that mesh current is flowing through each individual component, right? So it'll be 5 ohms times IC minus 6 amps. Connor, what do we see next? Negative 2IX, absolutely right. We see the negative polarity terminal of that dependent voltage source. Nick Parker, what comes next? IA minus IB. Absolutely correct. that's equal to 0. So notice here, when we wrote our KVL equation for our super mesh current A and mesh current C wind up getting positive signs, and all of the other meshes wind up getting negative signs, right? In our equation. So everywhere that we have IA is positive, everywhere that we have IC is positive, everywhere that we have IB is negative, and everywhere we have 6 amps, which represents ID, those all get negative signs as well. All right, so moving right along, KVL at mesh B. Hayden, what should be my first term? Negative 4 volts, right? We see the negative polarity terminal first. Carter, what comes next? 3 ohms times IB minus IA. Absolutely correct. Kennedy, what's next? Plus 2IX, because we see the positive polarity terminal of our voltage source next. So equal 0. All right, so let's look at things real quick here, right? We have 5 unknown quantities: IA, IB, IC, ID, and IX. And we have written 1, 2, 3, 4, 5 equations. So we have enough to solve it. Now I want to point something out to you guys here. We couldn't write a KVL equation for mesh D, even if we tried. And the reason I say that is because our super mesh equations are all about avoiding taking the voltage drop over a current source. When the current source is on the perimeter of a circuit, we can't write there's no loop that will enclose it because it's on the edge. So whenever we have a current source on the outside edge of a circuit, we're only going to get a current relationship equation out of that mesh. When we have an interior current source, like that 5 amp source, we'll wind up getting a super mesh equation as well that encloses it, as well as a current relationship equation. Does that make sense? All right, so we could throw these in our calculators and all that kind of stuff. You're welcome to do so. I've been talking for the better part of an hour, so I'm going to stop and let you guys get into your in-class assignments, as I think I've covered everything I wanted to cover today. If you have any questions about any of this stuff, Henry. If you have any questions about any of the example problems that we've worked in class today, any questions regarding the in-class assignments, or any questions about any of your homework assignments you want to flag me down and ask about, I'll be here for the next roughly hour. So by all means, let me know, and I'm happy to help.